My name is Carolina Garcia Baccino. I've been working with Andres in a postdoc since 2019 until 2021. And we've been working in two work packages of Smarter, and here I will present some part of the work that we've done. So basically I will talk about the work we did related to the detection of unrecorded environmental challenges. Okay, so I will go through 4 points. First one, I will go back to some important ideas that some of them Andres already mentioned them, and also Masoud, but they are important to keep them in mind. Then I will present directly the method, that is a data-driven approach, and the objective is to identify unrecorded environmental challenges from data that we can all have, that it's production data, we can say like that. Then the third part will be assessing the effectiveness of the method. And finally, we will work, or I will show some results related to the genetic part, the genetic analysis that we did related to this information that we recovered from the data. So first we will go through the background. Again, Andres already presented this, but it's an important idea to keep in mind. Animals are exposed to different things that they can be, for example, changes in the diet, management, temperature, weather conditions, etc. We have to bear in mind that they can all be acting together or not, or maybe some of them. And basically, they can have a negative impact on the productivity and also the welfare. So it's important to take this into account. Also, another important idea we have to keep in mind is resilience. We will work under this idea that when we speak about resilience, we are speaking about the capacity of an animal to be minimally affected when he's exposed to a stress, a disturbance. And this idea also of having the ability to rapidly recover from this stress. So some important ideas also. Animals can be exposed to heterogeneous and different conditions during their life. And also, it depends also on the species, but there can be little control of the environment. And given these conditions, it is necessary to select animals that are capable of maintaining their production performance, or at least modifying it as little as possible. So, a very important idea. It is very useful for us when there is an environmental challenge or a stress that affects the whole population at the same time, maybe, because it's a good opportunity to select for resilience. And also, another important idea is that environmental challenges happen, these stresses, but they are generally not recorded directly. And normally they are from a known source. We don't know where they come from. So what were the objectives we had? First of all was to develop a method that is simple and practical, and we can apply it directly to data that we can say that it's like normal data we can all have. And the idea is to estimate the probability that at a given date there was a stress or an environmental challenging occurring. And the idea to do this is by using the model of a mixture model of phenotypic variances, or some values related to this idea of the variance we will see specifically. Second, the second part is to evaluate the genetic determinism of resilience. Of course, taking into account this information that we were able to recover using this method that I mentioned in the first step. And finally, that I will go through this during all the presentation, is to go through a practical method using real data, applying these methods. So we will start with the method, how it works, and what is the basic idea that is behind it. So basically, first, what we have to know is what we are looking for. And here we have this idea that is very important from now on for this method, is that the effect of the stresses, what's happening when there is a stress on the performance of the animals. And basically, we can observe it indirectly through changes in variability patterns. And basically, to do this, we have to be able to have repeated records. I will go back to this idea because it's very important. But what are we talking about when we speak about changes in variability patterns? Well, basically here we have an example in which we have here the day, so it's an example that is not real, just to understand what's the principle behind. So we have 10 days, and here we have the feed intake. So here what we can see is that there were 2 days, day 3 and day 8, in which we can say that a priori something could have happened because there is an increased variability, in this case in feed intake. And this can be linked to this idea of a stress occurring. So that's basically the idea we will work on from now on with this method. This idea has been also reported, and there are also these 3 studies, for example, in which they report this kind of behavior, if you want, related to the increase in variability when some kind of challenge occurs. So another important idea is why we need to get or work with frequent records. Here we have an example where we have days after parturition and milk yield. And we can see that each dot in blue is 1 record, and we can see that they are very frequent. This enables us, as you can see, to follow the behavior of this production curve during time. But check what happens if we have less frequent data. Yes, we can have an idea of the general behavior of the production curve, but you can see that we miss up things, for example. Or maybe we get it here, so we will think that the curve has another shape. So that is why the frequent data enables us to follow, if you want, the behavior of the phenotype we are studying. So basically, what has been done before, there were several approaches, different studies presented related to this subject. And the idea was to identify variation, as I mentioned before, using high-frequency data sets. Again, working on this idea that this is related to the presence or of an environmental challenge or a stress happening. Many of them, and this is an important idea, involve the estimation of a target trajectory curve. That is, you have first to estimate the curve you expect of each animal, maybe, or maybe a mean curve, and then you can check for deviations from that curve. In the method I will present today here, we don't need to go through this step. And also this, again, in all these studies, they all agree on the fact that there is an increased variability when there is a stress or a challenge occurring. And also there is this idea that there is not a standard or a widely or default method that is applicable in different conditions or for different data sets. So again, the idea of showing or developing this method was to work on this as well. So basically, we will go first through this step, that is detecting the environmental challenges. So what's the main ideas that we have to take into account? First, that we can find, or we expect to find, 2 kinds of days, basically. Those days that were normal days, we can say, in which no stress was present, and days with stress. Again, the very important idea here, and I insist on this, is those days with stress, normally they will show high variance, and on the contrary, the days that were normal, they will tend to show low variance. The idea is to detect these variances fitting a mixture model to raw data. I will go I will present more detail related to that, And also it's important to mention that here raw data, it's generally speaking, of course, we will have to, in each case, adapt a little bit, for example, the script that you will see in the practical part to your case specifically. And on the output, normally, once we run the script or this method, or we use this method, we will find out that there will be two components of this mixture model. Again, one component will be linked to those days that were stressful, and the other component to the days that were not stressful. And here you have a little example of what you can find. There you can see that there is a mixture model in which we have two components. One is in red and one is in green. So we will get to see how we get there, but that's the basic idea. And in the end, finally, what we want to get is this posterior component membership probabilities. What is this? Basically, we want to know, to calculate which is the probability of a day being stressful or complementary, non-stressful. And second, the idea is to profit this information we recovered from the data, the raw data. I will show you an example with daily feed intake data. The second step, so it's to profit this information, these probabilities, to carry out a genetic analysis, to study the genetic determinism of resilience. So basically, we are able to incorporate this probability in the model. We will use the probability of being a stressful day, and we will use it as an environmental descriptor. How we will do that? Here you have an example. We will have probabilities of being a stressful day going from 0, that is no stress at all, till 1, that is maximum stress, is like the worst day. And you can see the logic behind this is that these are good days, we can see, related to the environmental conditions, if you want. And here we are in not good conditions, that is many or one, we don't know, stress was happening. So again, this will enable us to characterize the environmental gradient. And this idea, as you might imagine by now, is we will include this probability of being a stressful day as a covariate in a reaction norm animal model, as Andres showed before with the example of the temperature. Instead of using the temperature, we will use the probability of being a stressful day. That's the main idea behind all this. So to go a little bit further related to the first step that I mentioned before is how, now we will see more in detail, how we can detect these challenges from data. So basically here we have the main ideas. First, as we know, stressful conditions or challenges are linked to increased variability. That's a very important thing to keep in mind. And as I said before, we expect to have two components in the distribution. If we just plot a distribution, don't look here, just here, we can see something like this. This is an example, but it's something we can see of the data, for example. And the idea is that we can have two components in a normal mixture model. First one, normal days, no stress happening, and second, stressful days. Here we have how we can write this idea. We can, here, Y is our trait, our phenotype that we are studying. In the case I will show you after will be daily feed intake. And we will work with some measure of variability. Here we have the variance. We can work with others. I will show you later others. And that's important also because that implies that when you have your data, you should go through an exploratory step before analyzing and getting to know the data as well. I will come back to this idea. So basically, we can write this variance of the phenotype as a mixture. You can see here we have a sum of two parts. It's the two components. And we have alpha is the mixing proportion of the two component densities that we have here that are two normals. And when we fit this mixture, we can get something like this, in which, as I showed you before, we have two components, one in red, one in green. That is the main objective, we can say. We will see this with an example later. Once we have this, what we really want in the end is to get the probability of a day of pertaining to one or the other distribution. That is to say, in other words, the probability of that day being or not stressful. That's the main goal here. But first, of course, we have to fit the two-component normal mixture. Okay, and very important idea as well, as I mentioned before, that the mixture model is expected to be accurate with data that is frequently recorded. Okay, an important question here that it's also a very important thing to take into account. We can find out that there were some stressful days, but the question can be, okay, what happened during those days? And here the important idea is to know that that day, first of all, we could have, for example, I don't know, very high temperatures, and that is one stressor, but we can also have a combination of variables happening, I don't know, presence of humans, temperature, and another problem, a mixture, for example, of some of the examples that Andres mentioned before. Okay, so now we will go to the third part, that is assessing the effectiveness of the method. And to do so, we used a real data set that I will describe. Again, this is important to have in mind the structure of the data and at least have some expectations of what we can find. So basically here we worked with 951 Romaine male lambs, all with the same ages, around 12 weeks. They were all phenotyped for feed intake. That was a trait that was continuously recorded, and this was done using the automatic concentrate feeders. And this was done at the INRAE-Sapigné experimental farm. These phenotypes were recorded during different years. In total, there were 8 years, going from 2009 to 2016. And it's important to mention that all the animals within each year, that is within the same period of time, were tested under the same environmental conditions. That is to say, if we find one day that was stressful, we can assume that it was stressful for all. That's an important idea also. And the phenotypes were recorded during winter and during 8 weeks. So in total, we had almost 52,000 daily feed intake records. And we had also in the pedigree around 5,000 animals. And this is the data set we will work with in the exercise when we finish the presentation. So what we did first, as I told you before, an exploratory analysis of the data. Here is a very little summary, but the idea behind this is to show you that this helps to have an idea of the structure of the data, of what you can find, and if there is something there that you should notice. So basically here we have the consumption, we have the date for each year. And here we can see simply, and in not a very exhaustive way, that there were some days that maybe something could have happened, because we can see more dispersion, as you can see here, for example, or here, related to the consumption. But this is completely empirical, just to get an idea. Okay, so what we did after the exploratory analysis, of course, we did more steps this is just a summary as I told you. We assessed or worked with variation. We were working with daily feed intake. As you can imagine, we had very frequent records. That is to say, we could have around 10 or more records per animal per day. What we did is we calculated daily feed intake, that is, we summed up all the consumption for each day for each animal. So that is what I am talking about when I am speaking about daily feed intake here. And we worked basically with the coefficient of variation. Again, this enables us to work over the variation of these traits. Once we calculated that, and we will see it in the exercise, we fitted a mixture of two Gaussian distributions. That is basically what we've got. We worked with the natural logarithm of the coefficient of variation, as you can see there. And finally, once we fitted the mixture, we calculated the posterior component membership probabilities. Again, in other words, that is the probability of being a stressful day, for example. So here is what we got. We have the day here, and the important part, this is just information of what we have in the x-axis, and we have here two columns. That is the probability of pertaining to each of the components. First column is component 1, that is in red. Second column is component 2. So these are probabilities. What do we have here? For example, the probability that day 1 was a stressful day was of 0.58. Day 2, the probability of being a stressful day was around 0.80. And like that, we had a probability for each of the days. Here we can see in this plot, again, what do we have here? We have one plot per year for the 8 years. We have the day and the probability of having a high coefficient of variations, that is to say, of being a stressful day. So we can see, for example, in year 2, the second, third, and fourth day, they had a high probability of being a stressful day, almost, that is around 0.99. We found the same in year 3 and in year 7. This red line here is when the probability of 0.9. We just look to these days that were on higher than 0.9, the probability of being a stressful day. But there, we can see also that there were some days, for example, this day here in this year, that the probability of being a stressful day, that is to say, of having a high coefficient of variation, was 0.60 approximately. So there was also a little variability there. So what we did first, we recovered a little bit of data, because remember, this was done on an experimental farm, so there was some data, historical data, of some events happening during the studies. So basically, we went to the books and checked if we could find something that happened during those days. Basically, the conclusion was that yes, there were some records of some problems or some stresses happening those days that we found that they could be stressful. Other days that we found out that they could be stressful, there were no records, but that is normal. Normally, we don't have records of other things, but the production or phenotypic information. So basically, and another important thing that we found out is of all the days that we studied, around 4% of those days had a probability higher than 0.5 of being a stressful day. So up to here, we saw the part in which we present the method to detect those days in which a stress or an environmental challenge could have happened. Now we will go through the genetic analysis using these probabilities that I presented before. So basically here, as I told you before, we have this information for each day, a probability of being or not stressful. And the question now was, okay, how we take into account this when evaluating genetic determinism of resilience. So these probabilities, as I explained before, they enable us to describe the environmental conditions. And as you know already from all the presentations that there were before, we can use a normal reaction norm model, including these probabilities. And how we do that? Okay, in this case, we used this model. We have, first of all, here the daily feed intake, that is basically the information. It was in kilograms. And what we have here, it's a term that it's a combination between the year and the automatic concentrate feeder. Then we have a term that it's a regression on the day to take into account the effect of growing on the daily feed intake. And then we go to the part in which we have, in green, as you can see, A0 and A1. Okay, so A0 is the breeding value for the level of the daily feed intake. That is basically our classical breeding value, if you want. And this is important to mention, that is environmental independent. This is exactly the same as Andres mentioned before. And then we have this second part in green, that is A1, that is the breeding value for the slope. And as you can see, it's multiplied by the probability. So that means that it depends on the environment, that in this case is described by the probability. So as you can see, we have also included the probability in this term and here. This part of the model, we have this first term, PE0 and PE1. Basically, they are permanent environmental effects. And we have in the first part the intercept that is independent of the probability, and the second part that depends on the probability. And finally, we have the residual. So what we did basically is we fitted this model, and we also fitted another animal model, if you want, like traditional, we can call it, without the reaction norm terms. That is to say, without this term and without this term. Basically to compare and to answer to the question, is it worth it modeling like this, or we just can go with a simpler model? And what we did is to estimate covariance components using some of the programs of the BLAPF90 family. So here what we saw, basically we compared, we assessed the goodness of fit of both models, that is the simple one without the reaction norm and the complex one with the reaction norm. And basically what we saw is that the reaction norm model fitted the data better, and that basically using this information, that is to say this probability inferred from the data, was useful as an indicator for, or an environmental descriptor to include in the model. What we did also, and we will see that in the exercise, is that we estimated the breeding values for environmental sensitivity, that is to say the slope I spoke about in the other slides, and of course of the genetic potential of the trait that we were analyzing. Another result we got is that the level and the slope were negatively correlated. The correlation was around minus 0.46. And basically, one thing that we can say related to this is that if we select for increased daily feed intake, this can lead to an increase of the susceptibility, that is a higher slope or a higher sensitivity to stress, taking into account that we are speaking about daily feed intake. Another thing that we did is basically we were able to find that there were different patterns, if you want, of response. Here, if we focus in these 3 plots, we have each curve, it's an animal. So we had basically animals in which the breeding value didn't change much, we can say, with different probabilities or with different probabilities of being on a stressful day. So these animals tended to be less sensible, we can say. And then in red and in green, we had 2 different responses. The red one is basically, we can see that this breeding value tends to go down when the probability of being in a stressful day increases. And on the contrary, in the green case, the breeding value was higher, if you want, when the probability of being a stressful day was higher. Here also we have another result. There are also others in the study. You have a copy in the folder to download to see more details if you want. Basically, we have here still the probabilities of being a stressful day. And here we have the correlation between the level and and this is the breeding value at a given value of a probability. So basically, if you look here, when the probability of being a stressful day is 1, the correlation is around 0.2. So what you can say from here is that selection in a non-challenging environment, that is in the green part, let's say, would result in a very small progress, given this correlation, in a challenging environment. So what were the basic conclusions? First of all, related to the method, that it's a useful method, and in this case, in the example that I showed you, it was useful to identify challenges. It's also useful because it will give us the possibility of calculating these probabilities of being on a stressful day and then including this information when selecting or using or carrying out a genetic analysis. It's a general approach, so normally it can be applied to different kind of data. As I told you before, each case should be analyzed and adapted to each case. It's also useful for detecting the other challenges than meteorological, other kinds of stresses. And of course, well, as I told you before, they enable to detect stressful conditions that already happened through the data. Related to the genetic analysis, well, as I said before, the probabilities were useful to include in the model. They were useful to use as an environmental descriptor. We were able, using this information, to estimate breeding values for environmental sensitivity of the animals. As I said before, the negative correlation between the level and the slope shows that we can say that the animals that eat more are more sensitive to stress. And we also observed, as I showed you in the plot where we had 3 little plots below, is that there was a re-ranking of individuals according to the environmental gradient. And basically, this confirms or shows that there is a genetic environmental interaction. Okay, so thank you. I don't know if you have any questions.
phenotypes for the same animals of the same period to see if the stressful day can be seen on both?
No, we didn't, because we didn't have that information, but it's interesting. Yes. Yeah. Yes.
The record you used, was it taken during the course of this project or before the SMARTER project?
It was before, and the objective of the initial study was completely different. We took advantage of a data set that was already there to work on that.
Well, you seem not to present a shortcoming from your own analysis. What are the shortcomings of this method you use in running data? What are the disadvantages? What you think the model did not capture using this particular model?
Okay, I think that the first part is the strong part, if you want, is that this method you can apply it to any data set, if you want, with data that is most of the time available because it's data we have, that is production data, and it enables you to find out which days or which moments could have been stressful. Then, related to the information that maybe you can't capture, well, that will depend on, first of all, the amount of animals and information you have. If you don't have, as I showed you, frequent data or frequent enough data, that will be complicated to really detect things. Yes?
For the stressors, did you consider the type of, for example, stress, or you consider the level?
When you say,
for example, temperature, did you consider the level may be very high temperature or very low? Or you consider the different type of, for example, stress factors like temperature, maybe humidity was so high, for example, or there was some kind of activity being done on that day, maybe weighing the animals, or it was a combination of different kind of perturbations.
Okay, so to answer you that, first of all, is that we had partial data related to the stresses of each day, because as I told you, there were only some records on the farm. We didn't have records in this case of temperature or humidity, so in this case we couldn't do the link related to those variables. I will add that we did some other studies with another data set in which we had temperature records, and we found some link related to, let's say, we found that there were stressful days in those in which the temperature was high. But also to add, we found also other stressful days in which maybe the temperature was normal, we can say. So we can think related to that we are able to find or detect other perturbations than temperature, for example. Sometimes you can record them, sometimes you didn't even know them. You don't even know them, so.
Okay. In the data set, you have animals from 8 different years, and you mentioned that you assume that the period of the year across the 8 years will be similar because they were all from winter. But in a case that, for example, you might expect differences between years or across years, how much do you think that this could affect ranking the animals or identify animals that are resilient, not resilient?
You have to take that into account. And in fact, we did in the model, because if not, you are mixing things. Yes. Yes.
If they were female animals, do you expect the result to be different from this?
You have to take that into account as well. Yes. In this case, they were all male. That's why we didn't consider, because, yeah. Okay. Any other question? No? Okay. So now we can go to the part of the exercise. So if you check on in the folder to download, you should have this. I will go there. Okay, so this is the folder to download. If you go to this folder that is called Session 4 Exercise Real Data, there you will find, well, many things. I will go through the document that is called Challenge Detection PDF, but you can open, if you want and follow the code, you can open this file that is called Challenge Detection RMD. I will open to show you just in case. Why is not open? Ah, okay. Yes. This is the document. If you want to follow, I will go through the PDF, but this is the same version, just in R. And if you want to go running to see what you get in parallel while I speak, you can do that using this little button. Okay. So. Okay, so as you can see first, the first part, you have an introduction of the method to detect the challenges we spoke about. Here you have an introduction, basically presenting the data set and a little bit of its structure. As I told you before, it is important to have a little, at least, insight to know what we can expect. So that is why I added this part for you. The important things, well, some things I already mentioned, related, for example, to the quantity of animals. We can say that each group related to each year, we had around 120 animals, but there was a little variation related to that. And well, then you have some ideas related to the age and other information that you can read after. Okay, so first of all, what are we doing? First, we are removing everything that we have in the working environment with this command here. Probably you have already things from the exercise from before, so it's best to clean everything. And we are also loading the different packages that we need. Secondly, we will go and read the data. The data, it's in a file that is called datalams.txt. In that case, just to mention, there was a little addition or cleaning made before, just to remove, for example, records in which the consumption was 0 and some kind of little errors. So that data is already clean. Basically, when we read the data, we are setting the classes of each column, and we are assigning as well the names of each column. So if you see the first lines of the data, what we have here is in the first column, the animal. This ID, it's a fake one. Even if this data set is a real one, I just changed them with IDs that are not real. We have a date. We have a moment that is just a code to know in which moment of the date was the record taken. The intake, that is to say the amount of feed that the animal ate in this moment. And also the time of the intake. This is in seconds. That is the amount of time that the animal was in the automatic concentrate feeder eating. So as you can see, for the same animal, you will have many lines because he ate at different moments. So in this first part, what we can see, if you check the number of lines, we have around a little less than 1 million lines, and each line is a visit. So as I told you before, the idea is to work with daily feed intake. So here we have different moments during the same day of the animal eating. We have first to calculate the daily feed intake. As you can see here, there was an average of around 14 visits per day per animal to the feeder. So first of all, what I will show you here, it's an example for this data set. Of course, these steps will change and you will have to adapt if you want to run this on your data set. So here what we did is first setting the date to the format we want so that R knows that we are working with a date. Then we added a column with the year. We also set, the idea here was to divide the records in different periods of time that are the years I showed you before. We added as well the feed intake records. That is to say, we added the consumption on each per event, per day, per animal. And we also added a day number. This part of the code does all that. So if you run that part, you will get an object that is called big data. And what we have in big data is one line per day per animal now. So we have daily feed intake in each line. If we check what we have inside this object, here we can see the first line. Well, basically we have the animal, the date, we have the period. The period is the year. Here I put it 1, 2, 3, 4, 5 until 8. The intake here is in grams. And this is the amount of visits and the day. So as you can see now, we have one line per animal per day. This is a different animal, and well, the intake per day. Here I just, to check, I added this part that is table just to see the distribution of records per period, per year, just to check that we got something logical. There are many of these steps just to check and also to have more insight of the structure of the data. And what I did also here is adding a bar plot in which, it's not nice. Oh, okay. Basically is the number of days. Here they are all mixed up. All the years is just the checking points. The number of animals with records. So we can see that during all the years, all the animals got at least 45 approximately days with records, and there was some variability for each year, which is normal according to the information we had before. So we already, as I told you before, we calculated the daily feed intake. We will work with that. And here what we did is the calculation of the coefficient of variation, the variance, and the logarithm of these values. Here was, as I told you before, an exploratory point, moment, as you can see, because there were different options. We finally worked with the natural logarithm of the coefficient of variation. Still, I left this part of the code because this can be useful for you. You can work with, for example, the variance that depends on the trait and on your case, what you're doing. So basically, this part of the code will calculate all these values, as you can see here. The variance, the coefficient of variation, and the logarithm of these two values. So with this part of the code, we get an object that is called P2. If we check what we have there, where basically what we have is period, that is the year, the day within each year. And here we have, some statistic that is the minimum value, the intake, and also what we wanted, the variance, the coefficient of variation, and the logarithm of both values. And here comes the part of the mixture, of fitting the mixture that I showed you before. So here we have the code. You can go through the details here in the document. But basically, what we are doing in this part is fitting the mixture of normal distributions with two components. You have all the details, these function that is called normal mix EM, has different parameters. You can change or adapt according to each case. Here you have an explanation of all those that that we have used. And basically, as you can see, we were working with the logarithm, the natural logarithm of the coefficient of variation. So basically, if you run this function, here I stored the results in this object that is called mixMD L1. We can see what it has with a summary. And as you can see, well, we have some values here for the components 1 and 2. Here you have the explanation, which is of what is each thing. We have lambda, mu, basically the parameters of this mixture, sigma. And one question that was important to make sure was, are we okay working with 2 components, or maybe should be 1 or 3? Let's check that. So this section basically, So here basically, as it says here, is to make sure that we are working with the adequate number of components. Here you have some study in which you have more details if you want to read more about this method. And basically what we did is we have a test that here you have the code in which basically we will test a hypothesis of the order or that is the same, the number of components of the finite mixture model under, well, the null hypothesis. So the default value for this case is 1, starting from the case in which we only have 1 component. That is the first we will test. And as you can see, when you run this first test, you will get something like this that we are able to reject. So we reject this first hypothesis. We will test the following, that is having 2 components. So we run again the same thing. And here in this case, we are not rejecting. So this makes sure that we are okay with 2 components in this case. What else do we have? Well, once we have fitted this mixture, we can make a plot to see what we've got. This is the same plot I showed you in the presentation before. So what do we have here? We have the 2 components, basically the red one and the green one. And the main goal, as I told you before, was to calculate the probabilities of pertaining, that is, for each day of pertaining to each of the 2 components. So, important to remember, this is linked to 2 kind or types of days, those that were stressful and those that were not stressful. And here we have the section in which we calculate these probabilities. So basically, we can get them from this object we got already before that we saved here. Here the code is just extracting the posterior probabilities. And as you can see, here we save them in this object, and we can get a summary of this object just to know what's in there. And we can see that the second and the third column are the 2 components of the mixture. And here we can see, for example, the mean. We can see the minimum value that we've got and the maximum value. This is just to see what we have. Here you have some more information that you can check. And you can see that, for example, the mean of the probabilities of pertaining to the second component, The second component here would be the component linked to the stressful days was of 0.09. And that is logical because as we saw before from the results in the presentation, we saw that most of the days were normally not stressful.
Carolina,
Yes?
what would happen if it was the other day?
It's complementary probability.
No, I mean, if the day with big bias was the frequent one,
Yes.
it's probably 0.9, and the day with low bias was less frequent.
Then you should ask yourself what you're doing.
So then we need to admit that the farmer has normal days and then days when he becomes kind of maniatic.
Probably yes, that's the problem. Yeah.
Or if we find three components, then we need to get creative on how we interpret that.
In that case, well, we had at first some situations in which we were having three components, and it was a problem of how we were summarizing, in this case, the data. But that can happen and normally could be linked to some kind of problems. In the 3 or 4 tests that we did with independent data sets, we didn't have problems related to that situation. We only had one serious problem, we can say it like that, with one data set in which there were very few animals, so we were not able to fit directly a distribution. I think that that's the main problem. Yeah. Okay, so what you can do also later here, as I showed you before in the presentation, it was like keeping, just to see, those days in which we had a probability higher than 0.9 of being a stressful day. That is to say, those really stressful days. Of course, this level you can change it. You can keep those that have a probability higher than, I don't know, 0.7, for example, or as you have later, 0.5. Here, the idea was basically going further and to see what happened those days. So basically, we extracted that in this object that is called out09 to watch a little bit, specifically to see the period, that is to say which day, which year and which day, and go and see if we could find an explanation or not. And as I told you before, for some of them there was an explanation and for others there wasn't. Well, you can do the same thing as I told you before, but keeping those days with probability higher than 0.5 of being a stressful day. Is basically the same procedure, just you change the value here of the probability. And in this case, of course, we have more days. This could be interesting. Of course, that depends on the case and the objective of the study, but just to show you that you can go further and see what happened. Okay. Well, as I told you before, only around 4% of the days across the different years were found to have probabilities higher than 0.5 of being stressful day. And what we can do with this part of the code also is, yes, to produce this plot that I showed you before. Basically, what we have here are the probabilities. You can go through the details of the code and change whatever you want. If you want to change, for example, I don't know, the level, this line here of the probability you want to check, well, different things. Just to show you one way of watching this and going into more details if you need, of course. Of course, you can extract and, I don't know, just print one of those. That depends on what you want to do. In this case, we just showed the 8 periods. Well, here you have some of the conclusions written that I basically told you before. And now we go to the second part, that is the genetic analysis. Do you have any question until now of this first part? I will give you some minutes if you want to make this first part run, and if you have any questions, you tell me, and then we go to the second part in some minutes. That will be the genetic analysis. Okay? How to use and the parameter files and input files of BLAPF90. I will go through this document. As we said before, we will not run it, but it would be good if you can do it yourself later at home, just to check that it works. The idea now is to go through it quickly to understand what we are using as inputs and as the parameter file, and also to understand the results that we get. But it's also good to check later how to make the software run. So basically, some information to remember, because we will work with this now, is the model we will use. I will go through it fast again so that it's fresh. We have the phenotype, the daily feed intake. We have here a term in which we have a combination of the ear and the feeder. We have a regression on the day in this term. And here we have this first part that would be the breeding value for the level that is environmental independent. That is to say, here we will, in this term, we don't include the probabilities, but we do in the second term, in which we have A1. Basically, this is the breeding value for the slope, the sensitivity, if you want. And of course, here, this will depend on the probability of being a stressful day. Then we have the terms of the permanent environmental effects. We have the one that is independent of the probability, that is of the environment, and the second one that depends on the probability. And finally, the residual. Here you have the explanation in details. It's the same we just saw. So the idea is to run BLAPF90 plus. For that, we need a data file, the pedigree, and the parameter file. First of all, here we are working with a data set in which a real data set in which the IDs of the animals, they can be whatever. It can be an integer, or maybe it has letters also. Basically, what we do first normally is to run renum. Here it's already done. So that is why the pedigree information is already stored in this kind of file with this name. So we will go through the details a little bit of each file. First, we have the data file that if you check it, you have it available in the folder that is called to download. It has these columns, and here you have a detail of what is each column. So the first one is the daily feed intake. It's already is in kilo. That is the, yes, kilos. We have the second column, that is the ear duck. Duck is the automatic concentrate feeder. Then we have the third column is the animal. Here it's a fake identification. It's not the real one. We have the day. We have an extra column that I called it serious. It was just to check, so don't worry about this column. Then we have the year that goes from 1 to 8, as I showed you before. 7 is the duck, again, that's the feeder. We will not use it, but it was there just for checking purposes. And finally, the probability of being a stressful day. So here you have an example, but if we check the first line, basically what we are saying is that the animal 508 ate 1.5 kilos approximately of feed that was on the 10th day of the first year, just to understand what's the information that we have. Then we also need the pedigree file that I told you it has this name. If we check what's in there, you have here more details. If you check the number of lines, you will see that there are around 5,000 animals. That is normal. But as I told you before, only 951 animals have records, daily feed intake records. So what do we have here in each column? We have in the first column the animal ID. This is the renumbered ID. As I told you before, I ran before the renum software, so this is a new ID renumbered given by renum. The second column will be the ID of the father, already renumbered. The third one of the mother, as well renumbered. And then in the following columns, we have some statistics that we will not take care about in detail in this part, but just to let you know, here I put it some details for you to know what is in there. Just to mention, this is useful sometimes, that in the last column, we have the original ID of the animal. That is useful when we are working with real data. And here we will get to the parameter file. So basically, we have to translate this to how to tell this to BLAPF 90 plus to carry out the analysis. So here you have the format of the parameter file. Is exactly the same logic as you saw today with Andres and with Masoud. So we have first the data file. We should give the name of the data file that we saw before. The number of traits. Here we have only one trait. The number of effects that we will consider. In this case, there will be 7. Here we have to tell BLAPF 90 plus where is our observation. That is the phenotype of the trait that we are working with. And as I showed you before, it's in the first column of the data file. That's why I'm saying here 1. We will not assign special weights. So this line, sorry, is just at the end of the page. But here there should be a line empty when you run this parameter file. That is basically saying that we will not change weights or give more weights, as today Andres explained. And then we get to the part of the effects. First of all, you will see that you have 7 lines, 1, 2, 3, 4, 5, 6, 7. That's because we have 7 effects, as we said before. This should be logical. If you said before that you have 7 effects, here we should have 7 lines with something. So basically, in this part is where we should translate from this to what BLAPF 90 plus should do. So basically what we say is the first line, we are referring to the effect ear duck. Again, sorry, here is the automatic concentrate feeder. And basically what we are saying is that he will find this in the second column of the data file, and it has 44 levels. And is, here we have the class is cross-classified. Then we have in the second effect, it's in the 4th column of the data set, and it will be a covariate, 1 level in this case, and it's the day. Then we have in the column number 8, we have the probability of being a high coefficient of variation day, that is to say a stressful day. Here we will give it as a covariate, so here we put 1 level. And then we get to the part of this first one is the, we can say, normal additive, that is the animal. So you can see that it's in the 3rd column of the data file. It has 5,000 approximately levels, that is to say the number of animals that there are in the pedigree file, as we saw before. And it's a cross-classified. And here comes the tricky one, as Andres explained today. We have in column 8, remember, we have the probabilities of being a highly stressful day. And here we have to put the levels that in this case is the number of animals we have in the pedigree, because normally we will have a regression on each of them. Here we put a covariate because it's the type. And 3, it's, yes, the animal. Yeah. And then we have the parts, the last 2 is basically the same idea or the same logic as before, but with the permanent environment. So we have the first one, we are saying, okay, this is the column of the animal in the data set. The number of levels is the amount of animals we have in the pedigree file, and the type. And the same logic as before for the regression, we will say, okay, column 8 is the probability, the levels are the number of animals in the pedigree, and is nested in the animal. As Andres told you before, here we should add a residual value that we can give it just in this way. And then we have the first random group, as we can say, we can see here that it will involve which effects? 4 and 5. That is 1, 2, 3, 4, and 5. This is the number of effects you should put here. Here you will tell.
So if we have more than one group, do we separate them by comma? Do we write the next one?
No, you put it later. I will show you in 2 minutes. You put it later. So this is for these first 2. Well, it's a type additive animal. For this case, as Andres, the same thing that he showed you before, we are giving it the pedigree information. In which file? Well, in the pedigree file that we saw before. And here we will give the matrix of covariances that, well, these values, we estimated them before, they are already given here. And here comes the answer. When you have another group, you put it later. So you see, you include the other random group here that is related to the permanent environment effects, that if you see here are 1, 2, 3, 4, 5, 6, 7. That's why I'm putting here 6, 7. In this case, we will take it diagonal, and here we are giving it a covariance matrix with these values that we estimated them before. So, as I told you before, here you have the structure of the parameter file. You can try later to run it. If you succeed to do that, you will get this famous file solutions, that it will have this shape that you see here. It's the same logic that Andres showed you before. Basically, you have trait effects, level of the effect, and the solution. In this case, we only had one trait, so it's normal here you will see always 1. And then, well, for each effect and level, the corresponding solution. Here you have the explanation of what you will find. So, for example, as we saw before, for the year feeder, we had 44 levels. So the first 44 lines will be the solutions for each level of this effect, and so on. You follow the logic depending on the levels of each effect. So we are interested, of course, here you can go and see in details all the solutions. I will go to the parts that we are interested on, that is basically the breeding values. So you have the code there. If you want to try it, because you also have the solution files, you can read it. And basically, well, we can check that we read it correctly, it's correctly. And we can go and extract the solutions we are interested in. In this case, basically, we are interested in the part of the breeding values. That, of course, that will depend on the amount of animals that you have and effects, where you will find them in the solution files. Well, here in this part, you will see here it is explained, basically, but they are in these positions. And basically, we will calculate, not calculate, but, well, in one case, calculate, we can say it like that, the breeding values, if you want, in a situation with stress and no stress. As you know, when you have a stress, the extreme one is the probability 1 of being a stressful day. So in that case, I go back to this idea here. If it was not a stressful day, of course, in this case, mathematically, we can see that here the probability will be 0, so this term will not take it into account. But on the other extreme, if we are in a very stressful day, here the probability will be 1. And we can take into account, in that case, the level and the slope, of course, that is to say the two terms. So that is basically what I'm doing here. That is, that will be the values with no stress and with stress, and no stress, stress. And I just put them all together in an object that I call all. So here we can come and check what we have in each column. Basically, here we have a summary to get some statistics of these values. Here you can compare, for example, this is in a non-stressful situation, and this is in an extremely stressful situation, that is both extremes. And here you can come and extract different cases for different animals to see what happened with them. So for example, you have animal 441, that if you come and plot using this code, you will find this here. Basically what happens when it gets more complicated in terms of environmental conditions, you can see that the response, the breeding value tends to go down. Basically the plot that I showed you before during the presentation, the different patterns of response. Here there is another animal with a situation that it's a little bit different. There's almost no change in this case. And finally, you have this last animal that is just an example, just to check what we can find. That in this case, you can see that there is a little increase when the probability of being a stressful day increases as well. Okay, so basically that's all I had to show you for this part. Is there any question? Yes?
Can you use this GLUP F90 for the error study to see if it's significant increase between the 2 days?
GLUP F90?
Yeah. Do you have like an idea of the standard error or the...
But you mean related to the breeding values?
Yeah. For example, there between the 0 and 1 is not that different, so is it significant?
We did that calculation, and it's in the study. I didn't go through that because it's a little bit more of details, but you can see that what we checked was the amount, if you want, of change that was related to the standard deviation, to see really if this was significant or not, in a way.
So your question is, we get this breeding value for the slope. Is that, so it's, I don't know, 2. Is that too meaningful, or is or is really not accurate? So there is, maybe you can obtain a reliability for that thing, and from the reliability you can work out if that thing goes, the confidence interval of the slope up or down.
Other questions?
There was a question here. You know, it was about the columns of the way. You said that the column 8 you have the different variables.
The columns of what file?
Parameter file?
But yes, but that is related to a column of the data file. You're in this part of the effects? Yeah.
You said that column 8 has the probability, and then again column 8 has the...
So you are speaking about this and this?
Yeah, I think about the column 8.
Okay.
It's all at the same column.
Yes. Yeah. Other question?